Thank you very much, and good evening, Stratford-upon-Avon. The ABC of stellar evolution. You can see from the subtitle, we're looking at the birth and the life and the death of stars. So we know that when we look out into the universe, we see billions and possibly a trillion galaxies in the observable universe. All of them are probably made up of perhaps hundreds of billions of stars. And we're asking ourselves in this particular talk, how did those stars come to be the way they are? So we're not talking explicitly about galaxy evolution, but how do we start with a whole load of hydrogen? How do we get stars, and how do those stars evolve through their life to their death? So we're talking about birth, life, and death, and we're going to be looking at what's going on in the middle. This is not a physics lecture, so we're not going to be spending too much time on nuclear fusion, but that's obviously a rather key element of how stars work. We'll be looking at the key balance in every star, which is the balance between radiation pushing out and gravity pulling in. We'll be thinking about how the mass of different stars affects their lives. And we'll be asking the question, what happens when the nuclear fuel runs out? How does that lead to the death of stars? Do they end their lives with a bang or with a whimper? And what's left afterwards? So just to give us a sort of an idea, the sun is not necessarily a typical star, but it's somewhere in the mid-range of the sorts of stars that we see in the universe in terms of its mass and in terms of its size. So let's have a quick look at what our sun has been doing and will be doing. This is a timeline from the Big Bang at 0 through to quite a few billion years into the future. So that's where we are now, 13.8 billion years after the Big Bang, after the start of the universe. We think our sun formed somewhere around 9 billion years after the Big Bang. It condensed from a cloud of hydrogen, and we'll be looking in more detail at how that happens in just a short while. So that was about 9 billion years after the Big Bang, and our sun is basically middle-aged because the sun is about 5 billion years old, and we think we've got enough fuel to last another 5 billion years or so into the future. So very roughly speaking, the sun as it stands at the moment is halfway through its life. Once we get to that point on the right-hand side, the nuclear fuel, the hydrogen at the heart of the sun, will start to be used up, and then the sun will change. It will evolve in ways that, again, we'll see in a few slides' time. What's going to happen is that the sun is going to expand into a red giant phase, and then after that, when the outer part of the star has been blown away, what's left is a very hot core, which are described as white dwarfs. So that is very roughly the timeline of what is going to happen. These little cartoons here are not necessarily to scale, but it gives you an idea of the timeline in terms of how many billion years into the future we're talking. Once the sun becomes a white dwarf, it's effectively a white dwarf forever. No more nuclear reactions, so it just goes on and on and on. So what's going on at the heart of stars? Again, we're not going to go into too deeply the physics of nuclear energy, but basically in the heart of stars, the heart of so-called main sequence stars, hydrogen is being fused into helium, which means, roughly speaking, 4 protons, proton being the nucleus of a hydrogen atom, are being fused together to make the nucleus of a helium atom. And every second in our sun, 620 million tons of hydrogen is being converted into 616 million tons of helium, roughly speaking. So you can see there's a 4 million ton deficit between the two. That 4 million tons is being converted from matter to energy, and that energy is the energy that's keeping us lit and us warm. And of course, that energy is also being radiated, not just to the other planets, but of course in all directions of space. One thing to notice is that the 4 million tons that is used up is only a tiny fraction of the amount that's actually there. Less than 1% of the hydrogen in the sun is actually used to provide the energy that the sun is outputting. In that sense, stars are very inefficient devices. They're very inefficient machines. They only convert 0.7% or so of the fuel into energy. But still, that's enough to have stars last for billions, or in some cases, trillions of years. So stars, in a sense, are not just nature's way of lighting up the universe. They are fusion factories. They are designed to fuse light elements into heavy elements. A byproduct of the process is that we get energy out of them. And along the way, we get heavier and heavier elements building up as hydrogen is fused into helium, and then ultimately helium is fused into heavier elements. So the whole process starts with the lightest element, hydrogen. And you could say at this point, yeah, that's all very well, but where did the hydrogen come from in the first place? Yeah, a perfectly reasonable question, but that is not answered in this talk. That's a different talk about the beginning of everything, where all the hydrogen came from. It took the universe 3 minutes to make all of the hydrogen, and ever since then, that hydrogen has been feeding stars. But this talk is about what happens to the hydrogen, not where did the hydrogen come from. Different talk, maybe another day. So let's think about star formation, where they come from. You may be surprised to know that anybody can make a star. It's easy. All you need to do is to follow these 5 very easy steps if you want to make a star. You start with a very large cloud of hydrogen. Step number 2, wait. Step number 3, wait some more. Step number 3, just wait a little bit longer, and then you've got a star. In other words, you don't need to do anything. If you've got enough hydrogen, gravity will simply do its stuff, and it's inevitable that you will end up with a star. If you start with enough hydrogen, stars will be made. That's why it's so easy to make stars. That's why there's so many of them in the universe. Trillions of galaxies, each of which with hundreds of billions of stars. So you can work out how many stars there are, and that's just in the observable universe alone. So we know what star factories look like. Here's the Great Nebula in Orion, a huge cloud of hydrogen in which stars are being born, especially right at the heart there, as well as in other parts of the nebula. So what is it that triggers star formation? Well, there are large clouds of hydrogen in the galaxy. They're called giant molecular clouds. Why are they called giant molecular clouds? Well, they're called that for 3 reasons. 1 is they look like clouds. 2 is they're made of hydrogen. Can you guess what the 3rd one is? Yep, that's right, they're big. Okay, so there are huge clouds of hydrogen floating around called, very imaginatively, giant molecular clouds, or GMCs. So the question, I guess, is what is it that makes a GMC collapse? Why do these clouds collapse to make stars? There are various trigger mechanisms that can occur to actually make the stars start to form. One possibility is these clouds are floating around the galaxy. They're all going around the center of galaxies like everything else does under the influence of gravity. Every once in a while, these clouds might collide with each other, and when the clouds collide, the shock waves that result can send ripples through the cloud, which ultimately give rise to star formation. It's also slightly counterintuitive, but it's also possible to trigger star formation from the death of a star. In other words, when you get a particularly massive star dying, it can go supernova, and that can send shock waves through all of the interstellar medium, and if those shock waves go through a giant molecular cloud, that can trigger star formation as well. And the 3rd way of actually starting the whole process of star formation is to have galaxies collide with each other. Now, galaxy collision sounds rather cataclysmic when you think, is that the end of a galaxy when it goes smashing into another galaxy? Well, actually, quite the reverse. We now understand galaxy evolution a little better, and we realize that galaxies colliding with each other are actually a very efficient way of forming stars. So galaxy collisions are not in any way related to star death. They're actually related to star birth. So when we look at galaxies like this one is an isolated galaxy. Apparently it doesn't have any immediate neighbors. There are some star-forming regions in there. These little tiny dots of pink are hydrogen regions in which stars are probably being born. But if we look at galaxies which are interacting with each other, the famous Whirlpool galaxy interacting with a neighbor over here, perhaps you can already see that the amount of pink here is rather higher. So simple gravitational attraction between one galaxy and its neighbor the tidal effects between the two can give rise to a lot of changes in these molecular clouds, which give rise to more stars being born. So there is a lot of star formation in the spiral arms of any galaxy which is interacting with another. We see that in particular. Here's a small telescope's view of the antenna galaxy, where these two galaxies are interacting, and you can tell they're interacting because the tidal effects of one galaxy on the other is pulling out these huge tails, the so-called tidal tails, and that's what gives the antenna galaxies their name. But if we look in more detail with the Hubble Space Telescope, with what's going on in these galaxies, we see where these two galaxies are colliding, huge areas of very dusty environments in which there's an awful lot of pink. So again, huge molecular clouds are undergoing star formation when these two galaxies are interacting with each other. We know galaxy collisions are common simply by looking out and seeing with big telescopes that an awful lot of galaxies are interacting with their neighbors. Isolated galaxies are, in a sense, rather odd compared to the norm of having galaxies interact with their neighbors. And we are going to be interacting with Andromeda before too long. Andromeda is heading our way, and you can see the clock in the bottom right-hand corner. It won't be too long before the Andromeda galaxy comes our way, and the two galaxies, Milky Way and Andromeda, are going to pass through each other. That's the Triangulum galaxy watching from a safe distance as the two galaxies pass through each other. Very few stars are going to collide, possibly no stars at all collide, despite the two galaxies having hundreds of billions of stars in them. But the gas and dust in each galaxy will definitely interact with the gas and dust of the other galaxy, and it will perturb all of the molecular clouds in both galaxies, and again give a riot of new star formation. Eventually, the Triangulum galaxy is also going to be sucked in, but that's a little bit later. Notice the time scale here. It takes quite a few billion years for this collision to occur. But if we imagine what it would look like if we were here on Earth, here's a nice picture taken from apparently the middle of the desert. There's the beautiful Milky Way, and there's the Andromeda galaxy, a very nice target for astrophotographers with a telephoto lens. But because the Andromeda galaxy is coming towards us, it won't be too long before the Andromeda galaxy is so big in the sky, you won't need a telephoto lens to get a nice image of it. You're going to need a wide-angle lens to get a nice image of it. So this is after about 1 billion years. It's getting very big in the sky. After 3 billion years or so, the Andromeda galaxy is going to cover half the sky. And then a little while later, it will actually pass through. The two galaxies will pass through each other. We're not quite sure if it's going to be a head-on collision or a grazing collision, but certainly there will be a riot of new star formation when the two galaxies are close enough that you cannot tell whether a particular star originally belonged to the Andromeda galaxy or ultimately belonged to the Milky Way. So you can see this is a sort of artist's impression of what we think is going to happen at about 3.8 billion years into the future, 3.8 giga years. And now we can no longer tell where the Milky Way ends and the Andromeda galaxy starts, but we're certainly getting lots of areas of pink here, new star formation. And by the time the two galaxies are halfway through passing each other, the entire sky is going to be lit up with new star formation. So galaxy collisions are not the end of the line. They are simply a new revival, a new rebirth of lots of new stars in both galaxies. We can get an idea of what's going on if we think about what's actually happening in one of these star-forming regions. We can get an idea of what's going on by running simulations. So at first sight, you might think this is a large, I don't know, maybe a red giant star. No, this is a computer simulation of a large cloud of hydrogen. In reality, a large cloud of hydrogen will be highly irregular in terms of its shape. But computers prefer to deal with spheres and things like that. So this computer model simply says, let's take a large ball of hydrogen, let's make it spherical because that's easier, and let's take each little atom of hydrogen inside this huge sphere, which could be, let's say, 100 light years or so in diameter. Let's take each little bit of hydrogen and assume that it's got a slightly different temperature to its neighbor. Maybe each atom is moving slightly differently in a slightly different direction with a slightly different velocity. So let's give a little bit of variation to the velocities of each individual bit of this cloud, and then we just let the clock run and let gravity do its stuff and see what happens. And this simulation carried out at the University of Exeter was carried out a few years ago, and let's see what the simulation tells us over a period of a few million years. Some bits of the hydrogen drift away because they happen to be going outwards, not inwards, but gravity is starting to pull the core of the cloud together. And the hotter and denser it gets, the more yellow in this particular simulation of the color. If we zoom in a little bit to get a slightly better view of what's going on, we can see that it's getting yellower and yellower, and ultimately it's getting so dense and so hot under the influence of gravity, stars are being born. In various little regions of this cloud, stars are being born. Notice that some of the stars end up being born and stay fairly close to where they were originally born. Occasionally, when the stars are being born because of the high temperature and high pressure of the conditions in the cloud, some of them are given such a kick, they end up actually leaving the region completely. Some are moving quite slowly, some are moving quite fast. You can see it now starts to look like a popcorn machine. So many stars are being generated. We might have started with a cloud about 100 light years or so across. You can see a lot of the hydrogen from the outside. We're now doing a little spin, so you get a 3D effect. A lot of the hydrogen from the outside has been used up, but there's still quite a lot of hydrogen left. Even though we might have made thousands, possibly tens of thousands of stars, of which many are still close to where they were born, and quite a few have drifted away and are now no longer associated with that star cluster. We think all stars are born this way. Our sun appears to be on its own, but presumably billions of years ago it was born in a cluster. It was so long ago we can't tell which cluster we might have been born in. The galaxy has done a lot of rotation since then, and so we can't trace back our ancestry to say that star cluster over there was where the sun originally came from. But we can do simulations like this, and we can say, well, it looks like gravity plus a large cloud of hydrogen gives you a lot of stars. Does that bear any resemblance to what we think is actually out there? If we compare this picture, we can't always see where the hydrogen is if it's very faint and not being illuminated by stars. But if we look at the distribution of the stars generated in the cluster, lots of them very close to the core and a few a little bit further away, close to interstellar space. Does that bear any resemblance to real star clusters? Well, yes, it looks like the simulations give a reasonable explanation for why we see open clusters like this. Perhaps it's not quite the same for a globular cluster, but we have lots of examples of open clusters in our Milky Way galaxy that seem to have been generated by the process that we've just seen in a computer simulation. All stars, regardless of their mass and size and arguably how they were made, all stars are a result of a balance. If you think about what's going on inside a star, and let's not get bogged down in all the nitty-gritty detail, what's happening in essentially every star is that gravity is trying to pull the star in, and we have nuclear reactions at the core, which start with fusion of hydrogen into helium and ultimately the fusion of helium into heavier elements. But these nuclear reactions in the core produce radiation which ultimately pushes outwards because the radiation is trying to escape from the core and travel to the surface of the star. And all stars are a balance between these two opposing forces, gravity pulling in, radiation pushing out. And balance is an absolutely key property of anything we can think about in terms of stellar evolution. When the opposing forces are balanced, when gravity is balanced by radiation, the star is happy, the star is stable, the star is well behaved. But if those forces ever get out of balance, for whatever reason, the star must evolve. So as long as they stay balanced, the star is happy for billions of years, perhaps. But as soon as they get out of balance, something has to give, something must change as soon as you have an imbalance. And I would argue that essentially all the aspects, or at least many aspects, of star birth, star life, and star death can be considered in terms of balance and two other factors, and that's why I've come up with this idea of, you could argue that everything to do with stellar evolution is based on three different concepts, the first of which is balance. So let's look at what I think is the ABC. If you want to fuse hydrogen, hydrogen is effectively a positively charged proton. Let's ignore what the electron is doing. Let's assume the electron of hydrogen has been stripped away, so the nucleus of hydrogen is just a proton. If you want a proton to fuse with another proton, they're both positively charged, and we know like charges repel. Therefore, two protons don't really want to get together. If you want them to fuse together and make something heavier, you have to overcome the fact that they are both the same charge, and therefore they want to repel each other. So if you can get your medium, whatever it is, your gas, if you can get it hot enough with high enough pressure, you can get these protons close enough to fuse together, even though they're both positive and they're both trying to repel each other. If you get the gas hot enough, you can accelerate the fusion process. So I would argue that heat, or at least high temperature, let's not bother about pressure for the moment, but high temperature give the particles a lot of energy and get them really moving. High temperatures will accelerate the fusion process. That's the A of the ABC. The B of the ABC we've already seen. Balance. That is key to any star. If they're in balance, if the forces of radiation and gravity are in balance, the star is happy. If they get out of balance, things must change. So that's the A and the B. What is the C of the ABC? The only other concept you need to understand why stars change is compression produces heat. In other words, anybody who's ever pumped up a bicycle tire knows that. When you compress the air and put it into a bicycle tire, the pump gets hot and the tire gets warm, because whenever you take a gas and compress it, it gets hot. So that ABC, as we'll see shortly in a few slides' time, actually can be used to understand how and why stars evolve. A for acceleration, B for balance, C for compression produces heat. Now, the actual details of that will depend on the mass of a star. Let's just remind ourselves that if we looked at a classification of stars where we classify them by the luminosity on a vertical scale here and the temperature, the surface temperature on the horizontal scale, from cool on the right to warm on the left, we can classify essentially all the stars that we can see. There's the sun, roughly speaking, in the middle. This luminosity scale is on a scale of multiples of the sun's luminosity, hence by definition the sun is at 1, and the surface temperature of the sun is a little under 6,000 or so Kelvin. So that's a reminder of where the sun is, and we have obviously lots of other types of stars in this so-called Hertzsprung-Russell diagram. But what's important is that when we look at all of these stars, they all have different masses. There are very massive stars at the top and very low mass stars at the bottom. And that is key to the way that they evolve. So let's have a look at some examples. We're not going to go through every conceivable massive star, but let's just look at massive stars and less massive stars. If we deal with a high mass star, and high mass, we're always using the sun as a sort of yardstick, if you like. High mass means stars that are much heavier than the sun. They have a lot of fuel because they're very massive. So you might naively say, well, if there's a lot of fuel there, presumably they will last forever. They'll have very long lifetimes. But in fact, it's the opposite. Because the gravitational forces are so strong, because there's so much mass there, the gravity is very strong, you need to use up your nuclear fuel at a really prodigious rate in order to balance that. Remember, a star has to stay in balance. So if you want to balance that gravity, you need a lot of radiation, so you need to use up your fuel really fast. Even though you've got a lot of it, it actually doesn't last as long with a high mass star. So the nuclear fuel must be used very fast. So compared to the sun's lifetime of a few billion years, a very high mass star might only have a lifetime of perhaps a few million years. A million years sounds like a long time, but of course, if you think about the evolution where we have come from, dinosaurs were roaming the earth tens and hundreds of millions of years ago. So a few million years for a star is not long enough to provide the heat and light for a planet for life to evolve. So a million years is actually a very short time as far as stellar evolution is concerned. So that's what's happening with very massive stars. If we take the other end of the spectrum, what happens if we generate a star which is relatively low mass? Again, we might assume, well, there isn't much mass, so there isn't much fuel. Presumably it can't live that long. Well, no, because the gravity is very weak, you don't need to burn your nuclear fuel very fast. You don't need to generate a lot of radiation to counter the gravitational forces, to maintain the balance, and hence, even though there isn't much of it, the nuclear fuel actually lasts an awful long time. If we were to take, for instance, a star with a mass, let's say, for the sake of argument, 1/10 the mass of the Sun, if we start with a mass of 10% of a solar mass, how long would the star live? Well, we assume it would live for, the calculations tell us, possibly trillions of years. So long that we don't actually know because we've never seen it happen. The universe is only 13.8 billion years old. So even a star that was made very early in the universe, if it was low mass, its lifetime would be so long it would live for many, 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 many billions of years into the future, possibly even trillions, possibly tens of trillions of years into the future. So that's a calculation, but we can't observe it because that time scale is simply too long compared to the age of the universe. I've been talking about mass, and mass is key. Heavy stars live differently. They have short lifetimes, and low mass stars live for an awful long time, and they die in different ways, as we'll see shortly. But just to take a little bit of a detour, mass is critical, and we know that mass can vary from stars that are perhaps even less than 10% of the solar mass, the mass of our Sun, to stars that are more than 10 times as massive. So here I've been rather generous and said mass can vary from maybe 100 times less than our Sun to 100 times more than our Sun. We're not too sure about those limits. We think that maybe stars in the early universe had very high masses. People are still arguing about whether that's right or wrong. But it's certainly not a huge variation. It's probably at least a factor of 10, possibly a factor of 100 compared to the mass of our Sun. But if we look at the size, i.e. the radius or the diameter, that can vary by substantially more than simply a factor of 10 relative to our Sun. And just to take a little detour, let's just see how much the sizes of stars can vary. To give us a sense of scale on the small end, let's just start with a few objects we know, some objects in the solar system, not in order of their distance from the Sun, but in order of their size. So Mercury, Mars, Venus, Earth. Let's take the Earth from the right-hand end of that panel, and let's put it into the left-hand end of this panel. So there's the Earth, and then we can see the ice giants, Neptune, Uranus, and then the gas giants, of course, Saturn and Jupiter. So that gives us a sense of scale. Now we're going to do the same thing. We're going to take Jupiter from the right-hand side and put it on the left-hand side of the next panel. So there's Jupiter. And you can see that the smallest star, which in this example is Wolf 359, the smallest star, one of the smallest stars we know of, is not that much bigger than Jupiter. So that's why occasionally people say, Jupiter, it's a bit like a failed star. If it was a bit more, if it was a bit bigger, if it's a bit more massive, it would be almost enough to make a star. There's our Sun, substantially larger than Wolf 359, and of course substantially larger than Jupiter. So that gives us an idea of, okay, that's what we mean by a small star, a star somewhere between Jupiter-sized and our Sun-sized. What's the star on the right? That's Sirius, and you can see that that's a little less than perhaps twice the diameter of our Sun, a volume that's considerably larger, maybe 5 times the volume, and something a little less than twice the diameter. Let's do the same thing. Let's take Sirius and then put it on the left-hand side of the next panel. So there's Sirius. Remember, the Sun is smaller than Sirius. And as we go up, we see Pollux, Arcturus, Aldebaran. Now we're talking about really big stars. Remember, these don't necessarily have a mass which is hugely greater than the Sun, but their diameter is getting now somewhat ridiculous. Aldebaran is huge compared to Sirius, and Sirius is larger than the Sun. But we're not done yet. There's Aldebaran, which already looks like a ridiculously large star. Let's take Aldebaran, put it on the left-hand side. There's Aldebaran. And now we have Rigel in the constellation of Orion, and that Antares and Betelgeuse. And you can see why Antares and Betelgeuse are considered such huge supergiant red stars. Their diameters are orders of magnitude larger than Aldebaran, and remember how large Aldebaran looked on the previous panel compared to the size of Sirius, which is larger than the Sun. So Betelgeuse probably coming towards the end of its life, Antares possibly the same, absolutely huge, but not necessarily the largest star that we know of. Let's take Betelgeuse, put it on the left-hand side. There's Betelgeuse. Now we're getting towards the limit, because now we're looking at stars that are larger than Betelgeuse, but not perhaps by a factor of 10. VY Canis Majoris, when I put this slide together, was the largest one that had been verified. It might be in the last couple of years they found a larger star. But VY Canis Majoris was considered one of the largest at the time. So you can sort of figure out what's going on. If these stars are huge, but they're not actually much more massive than the Sun, then they must be much lower density. Yes, sir?
Where are the Wolf-Rayet stars in this picture?
I can't remember what size they are, but it's considered that most Wolf-Rayet are considered to be precursors to supernova, so we're talking about something comparable to Antares and Betelgeuse. Beg your pardon? Mu Cephei, I think it is, yes. Yeah. So it possibly is of limited benefit, but we could, if we wanted to, compare VY Canis Majoris directly with the Sun. Obviously, it's going to be a huge difference. So there's the Sun. There we go. Okay. And there's VY Canis Majoris. And if you're having difficulty picking out VY Canis Majoris, there it is. And this, by the way, is an exaggeration. I'm not exaggerating the size of VY Canis Majoris. I'm exaggerating the size of the Sun. Because if I put the Sun to the correct scale, the Sun would actually be less than 1 pixel. And it wouldn't actually show up on either my screen or this projector. So the actual size ratio is really, really enormous. But remember, that's not what determines stellar evolution. This was just a little bit of an aside. What determines stellar evolution is the mass. And the mass ultimately leads to the different sizes that we see here. So we know that the most massive stars burn their fuel very quickly and have short lifetimes. The least massive stars live longer. But we still have the same question. Yeah, okay, they might burn their fuel at different rates, but what happens when the fuel runs out? That still is the fundamental question when we're thinking about stellar evolution. So we're talking about nuclear fusion, but a lot of nuclear physicists still talk about fusion as a burning process. It's not burning in the sense that coal is burning in an oxygen atmosphere, but it's still occasionally called burning to say if you're burning hydrogen to make helium, it's a nuclear process, but that word is still used rather loosely in this particular context. And remember, this is just reiterating those numbers I said earlier. For the Sun, 620 million tons of hydrogen is converted into 616 million tons of helium, and the 4 million tons that is lost, E equals mc squared, 4 million tons of mass multiplied by the speed of light squared. That gives you all the energy that the Sun emits in 1 second. So fusion of hydrogen into helium is actually very inefficient in the sense that it's only efficient by 0.7%. 0.7% of the fuel is actually used to produce the energy. The other 99.3% of the mass of the Sun is still there after the fusion process. In other words, just ignoring some of the fine detail, you can say that if you start with a certain amount of mass when the Sun is born, 10 billion years later, after it's been radiating heat and light for 10 billion years, 24/7, 99% of it is still there. 99% of the mass of the Sun is still in the Sun after 10 billion years. It's not shrinking day by day because the nuclear fuel is being used up. The process is so inefficient, most of the mass is still present. But we can still ask the question, yeah, okay, but when it comes to the point where all the hydrogen is gone, or most of the hydrogen is gone, what happens as we get to the point where most of the hydrogen has disappeared and we can no longer reliably fuse hydrogen to make helium to release energy? That's where the ABC, I would argue, actually gets quite useful, because with the ABC, we can go through step by step and we can say, yeah, that's what you would expect to happen when the fuel runs out inside a star. When the hydrogen runs out, or at least starts to run out, I suppose I should say, the radiation is going to drop. The nuclear fuel at the center is no longer producing the same amount of energy. So if gravity is pulling in, radiation is pushing out, but the radiation levels start to drop because we're running out of hydrogen, then we are in an imbalance situation. We no longer have the radiation pushing out balancing the gravity pulling in, because now gravity is stronger than radiation because the radiation has dropped. So the star is no longer in balance. There's the B of the ABC. What happens then? Well, the star will compress because the radiation pushing out isn't going to beat gravity, so the star shrinks. If the star shrinks, what happens when you compress something? When you compress something, it gets hotter. So the compression is going to heat the core to a higher temperature. And what happens when you heat the core to a higher temperature? When things get hotter, you accelerate the fusion process because you're overcoming the repulsion of protons who don't really want to get too close to each other because they're both positively charged. And you can either start to burn more hydrogen, or you can start to actually fuse helium into heavier elements. But regardless, if you accelerate the fusion process, you will increase the radiation, and the radiation increases, brings the star back into balance. Balance is restored. So you get out of balance, which produces compression, which accelerates the fusion process, which brings you back into balance again, and in principle, depending on the mass of the star, this cycle can go on. When the helium runs out, what's going to happen? It'll get out of balance, it'll compress, it'll accelerate the fusion of heavier elements, and you'll be back in balance again. What happens when the next fuel runs out? It'll get out of balance, it'll compress, it'll accelerate the fusion of still heavier elements. In principle, this ABC cycle will continue, not necessarily forever. It only continues for a finite number of cycles, but this ABC allows us to understand why things change, for instance, why the sun will change when it gets to the end of its hydrogen fuel. So this is our friend Mendeleev and the periodic table of the elements. That's a little too frantic, so let's just get rid of some of that color there. So we've been talking about hydrogen, the first element in the periodic table, being fused into helium. And if you could continue with this process, this ABC, over and over again, you could then start fusing helium into carbon and carbon into other things. You will end up with carbon and oxygen and neon and various other elements in the periodic table, but only until you get to iron. You can fuse elements, you can fuse light elements, and when you do so, energy is released, but only up to iron. For reasons that I'm not going to go into, nuclear physics tells us that when you fuse elements up to iron, you release energy. But if you want to fuse elements above iron, heavier than iron, you have to put energy in. So stars cannot fuse any heavier elements in order to generate energy, which then gets distributed to the rest of the solar system. So if the insides of stars can't fuse elements beyond iron, then where does cobalt and nickel and copper and zinc and silver and gold and lead, where are all these other elements coming from? We know that the Earth's crust contains, roughly speaking, 100 elements, a whole load of elements lighter than iron, admittedly a lot of them, but we also know that we've got a few elements heavier than iron. The Earth's crust is relatively lightweight, but we know that silver and gold exist. We know that lead exists. Where does this come from? So, just to recap, we know that light elements fuse up to iron. And for reasons I'm not going to detail, when we look at elements fusing up to iron, it's a release of energy, but when we're looking at elements beyond iron, we have to put energy in, and so it's not a mechanism by which stars can generate heat and light, because we need an input, it's not an output of energy. So where did the heavy stuff come from? Well, we have to look beyond star life. We can't just rely on the ABC telling us this is what's actually happening and we're fusing hydrogen to helium, etc., because that only works up to iron. If we want to explain what happens beyond that, we have to look at star death. So the medium mass stars, and medium mass means something comparable to the sun, not necessarily as light as Wolf 359, not as heavy as a really massive star, many times the mass of our sun. It's possible that for a star similar to our sun, gravity is simply not strong enough to hold on to the outer layers. When the hydrogen starts to get used up and we go through the ABC, we're out of balance, so we compress and it heats the core up. It might be that the heating the core up produces enough radiation to puff out the outer atmosphere of the star. It starts to swell up, and we end up with a red giant. So it's part of the ABC, but trying to work out what happens next is not necessarily part of the ABC. We know the hydrogen is running out. We know compression will heat things up. What happens next will depend on some of the details of what's going on inside the star, how energy is being converted from the core or transferred from the core to the surface of the star. But we can sort of understand that if compression produces heat, that heat might radiate outwards and carry the outer atmosphere of the star to higher and higher levels, especially if gravity is not strong enough to hold it back. For more massive stars, gravity can hold on to that outer layer. But for stars like our sun, the gravity simply isn't strong enough to hold on to that outer layer, and the whole star swells up into a red giant. And the red giants are there. Remember, the sun is over here, so red giants are higher up. Remember, this is luminosity, and this is temperature. So it's to the right of the sun, because that's a cooler surface. As the star swells up, the surface cools down. So a red giant might only be something like 3,000 Kelvin, but it's more luminous simply because it's a larger surface area. It's not as hot. The amount of light coming from each square meter of the surface is rather less, but there are so many more square meters just because red giants are so big. And so the luminosity is higher. Higher luminosity, even though they are cooler. It is possible, depending on the details of how the stars evolve, that the fusion of hydrogen to helium and then ultimately the fusion of helium into heavier elements can get rather unstable. And again, we're not going to go through the details of exactly how that works. That is still the subject of a lot of research. But if the outer layers are given enough energy, then gravity simply cannot hold onto them, and the outer atmosphere of the the star, similar to the sun, can be sloughed away. And it can lead to the formation of a planetary nebula if the outer atmosphere of the star simply, gravity cannot hold onto it, and then it drifts into the interstellar medium. What's left behind when you take a star like a red giant and remove the outer layers and let that drift away into a planetary nebula, what's left is the core of the original star, which is what we call a white dwarf. And here's the white dwarf down here. They're called white dwarfs because their surfaces are quite hot, because they are the core of the original star, so their temperatures are much higher than the sun. But notice the luminosity is much lower. They are lower down in this diagram rather, simply because white dwarfs are relatively small. They're very hot, but they're very small, and hence their luminosity is rather low, even though their surface temperature is rather high. The atmosphere that's sloughed off, you can perhaps see in this example why you might call these planetary nebula. Nothing to do with planets, but some planetary nebulas, especially seen through small telescopes, can definitely give the impression of something that looks a little bit planet-like, which is how they got their name originally. And despite the fact that historically we now know that that is inaccurate, the expression, the labeling has stuck. So some planetary nebulas might look beautifully symmetric and spherical, but some planetary nebulas definitely not. Understanding why the outer part of a star sloughed off into space might end up looking like this. Again, it's a topic of research. We assume it's related to the way the star is rotating. Why exactly you get these very intricate structures for some planetary nebula is still a topic of some research. So if the gravity is not enough, like for a star like our sun, the outer atmosphere can be sloughed away, shrugged off. But if we're talking about a high mass star, gravity is so strong it doesn't allow those outer layers to be lost effectively. And so the whole process of hydrogen to helium, helium to carbon, carbon to heavier elements, that will continue on for high mass stars, simply because gravity is able to keep everything in the same place and you're not continually losing matter to the interstellar medium. So we end up with hydrogen being converted to helium, and then carbon, neon, oxygen, silicon, etc. So we end up with shells of material, each of which is fusing into heavier and heavier elements. So it gets very complicated, and understanding the internal structure of these high mass stars, again, the details are still to be worked out. But it's still obvious that when you reach iron, you can keep fusing until you get to iron, but then you cannot, by this process, go any further. Even in a very high mass star, you still are stuck when you get to iron. When you reach the point where iron can no longer generate radiation, because it can't fuse, it can no longer generate radiation to push out, to balance the huge gravity that's pulling in on these very high mass stars, then the core undergoes a catastrophic collapse. And it can be very, very fast when it actually happens. The core collapse supernova can occur in a matter of seconds when the core basically is no longer able to support the rest of the star. So the system collapses, the core is crushed under the gravity of all the overlying layers, and a shock wave effectively rebounds off the core and blasts everything else, all of the outer layers, into the interstellar medium. And the result is a supernova remnant, where a huge fraction of the mass of the star has been blown away into the interstellar medium. This is a Hubble Space Telescope picture from 2005, which is getting on for 20 years ago. We know from historical records that this was the result of a supernova that was seen in 1054, so this is about 1,000 years old. And it's very nice that this has now been revisited by the James Webb, and if we compare the Hubble Space Telescope picture of the Crab Nebula with the equivalent from the James Webb, I'll flick between the two. So that's the Hubble, that's the James Webb. I'll see if I can do this backwards and forwards. If you pick out one particular feature, like this feature over there, if I go backwards and forwards between the two, these are very carefully aligned, by the way. The stars are in the same place. If I go backwards and forwards, you can see that the nebula is actually slightly larger now than it was 20 years ago. That's 20 years ago. Now, 20 years ago. So the nebula is a few percent bigger. But remember, it went off about 1,000 years ago, and we're looking at a 20-year difference. A 20-year difference of something that's 1,000 years old, that's a couple of percent or so. So it's no surprise to find the nebula is now a couple of percent bigger. So we tend to think of everything out there in the universe as being somewhat static. We don't think of the Crab Nebula as being an evolving structure, but we're now in the position, because we have decades of data and decades of images, that we can see this thing change. And if we wanted to, we could image it year by year and see how this supernova is changing. At the moment, people are analyzing the Webb images. You can see this sort of wispy, milky structure around here. This is thought to be electrons that are accelerated by the magnetic fields coming from the pulsar right at the middle here, because the neutron star that's left, I'll come to the details of this in a minute, but the supernova has ejected most of the material and left a very compact star in the middle there who's got a very strong magnetic field, and we're seeing some of those effects by this glowing of the electrons radiating energy via a process called synchrotron radiation. And by looking at different wavelengths, we can get an idea of what particular elements are in the Crab Nebula. We determine something about the star that went supernova and the amount of material that's being redistributed back into interstellar space. You can do a back-of-an-envelope calculation if you want to, simply understanding Newtonian's gravity, and say if gravity is holding a star together with a mass of, let's say, 10 times the mass of the sun, you can calculate how much energy does it take to rip that star apart. Doesn't matter what the process is, you can simply say, if you've got a star of this sort of size, it takes that much energy to tear it apart. And that means nothing to anybody but a physicist who works in the units of joules. But you could convert it and say, well, imagine the total energy output of the sun, not just the amount that arrives on Earth. Think of the total amount of energy being radiated in all directions by the sun, 24/7, every second of its 10 billion year lifetime. If you take all of that energy, integrated over 10 billion years, that's the amount of energy which is released in a supernova in a few seconds. So you can see that it is truly enormous. If you imagine 10 billion years worth of energy released in a few seconds, you realize that calling it an explosion, that word in English just isn't enough to get across just how much energy is being released in such a short time. But it is precisely the reason that that much energy is released when the shock wave comes out and blasts all this material out into the interstellar medium. It is that huge amount of energy which is required to tear a star apart. It's that energy which allows you to start fusing things beyond iron. You can't simply take iron and compress it and get energy out, but if you blow the star to pieces with enough energy, then that process can take iron and fuse it into heavier and heavier and heavier elements, probably elements way beyond the periodic table that we can see, but ultimately they will radioactively decay into the sort of elements that we see in the world around us. And all of this material is ejected into interstellar space and then enriches the interstellar medium, ready for another generation of stars. So the heavy elements found on Earth were made in a supernova via the process I've just said. It's also possible that some heavy elements are made by, for instance, stars colliding with each other, but we know that supernovae are capable of generating very heavy elements. And because these elements exist on Earth and exist in the solar system, we know that the sun was not simply made out of hydrogen and is burning helium. It must have been made with heavier elements in the mix. In other words, it was made from a large cloud which was mainly hydrogen, but must have had lots of other elements in it because we see them in the Earth's crust. So we know that stars must have been born and lived and died before the sun came along. It's difficult to tell how many generations of stars were born, lived, died, reseeded the interstellar medium with heavier elements, and then more stars were born and lived and died, and again dispersed the heavier elements back into the interstellar medium. How many generations? We don't know. It's definitely more than a few. Whether it's more than a few dozen, it's difficult to say. But remember, the sun was born many billions of years after the Big Bang. There's been plenty of time for stars to be born, live, and die, especially if their lifetime was measured in millions of years rather than billions of years. Plenty of time for those generations of stars to generate the heavy elements which we see around us. If a supernova crushes the star's core and rips everything else in the outer atmosphere into the interstellar medium, what's left behind? Well, generally speaking, we would expect it to be a tiny thing, not the size of a white dwarf, which might be about the size of the Earth. The remnant of a supernova will be something only a few kilometers in diameter, not tens of thousands of kilometers. It'll be something like a neutron star. A neutron star will be kilometers in size, will have extremely strong magnetic fields, which is why we see synchrotron radiation in nebulae like the Crab Nebula. And if the neutron star is radiating, because of the magnetic fields, it is common to find a lot of electromagnetic radiation coming out in the polar regions of an object which has very strong magnetic fields. If the object is rotating, then it is possible to pick up the radio transmissions, especially if the radio transmissions are at an angle to the rotation of the star itself, because it behaves like a lighthouse, sweeping a beam of radio waves out into the universe. And if we happen to be in the right place, we can pick up those radio waves. And that's precisely what a pulsar is. It just fortuitously means we've picked up the radio transmissions of a spinning star, and hence we're picking up a variation, a modulation of the output of that star as a function of time. And we can hear these if we convert the radio waves into a sound wave to give us an idea of what it sounds like. We can listen to various stars. Let me just check. I seem to have put the volume down for some reason. So this is a pulsar with a period of 800 milliseconds. So that means this neutron star is rotating roughly once a second. It's got something like the mass of the sun. Our sun rotates once a month. This is a star with a similar sort of mass, but rotates once a second, or a little faster than once a second. This is the Velar pulsar, which is a period of 89 milliseconds. Again, a star with the mass similar to our sun, but with a period of something like a tenth of a second. We can go up faster still. The pulsar we saw at the center of the, or implied at the center of the Crab Nebula, a period of 33 milliseconds. So this is rotating 30 times a second. Again, all of these stars will have a mass similar to the mass of our sun, and it's almost impossible to imagine a mass that large spinning 30 times per second. By no means the fastest pulsar that we've seen. 5 and a bit milliseconds. So this is spinning 200 times a second, to the point where we can no longer hear individual pulses, and it just sounds like an irritating squeal. And there's one more, if you can stand it, and that is an even faster one, 1.5 milliseconds, so something like, 600 revolutions per second. This is getting very close to the point at which the surface of the star is moving close to the speed of light. It is very difficult to get anything to spin any faster than that, because you're literally getting too close to the relativistic limit. I've said there the period is 1.5 milliseconds. That's not strictly true. The period is actually 1.5578064488727 milliseconds. And it is known that accurately. These periods are known to phenomenal accuracy, because we can observe them not just for 1 second and count how many oscillations they've done. We can count them for weeks or months or years, and then we can work out their frequency very accurately, their frequency and their period. That means we have an excellent way of checking our atomic clocks, because they are extremely stable systems. We occasionally see glitches, which is changes to the star itself, but on the whole, they are very reliable. There are lots of them in the sky, and we can cross-check against lots of pulsars to check our atomic clocks. Because there are lots of pulsars in the sky, they are actually being used also to work out whether or not there are gravitational waves moving through the universe, because that will affect the timing of pulsars. And so if we check the timing of pulsars in different parts of the sky, we can work out whether gravitational waves are moving through the region between us and the pulsar. So different aspects of research is being done using pulsars as very accurate timekeepers. I'm not going to say an awful lot about the other possibility, and that is very massive stars, when they die, as well as sloughing off their outer layers, it is possible that the core is compressed so much that we end up with a black hole. I gave you a talk on black holes a little while ago, so I'm not going to go through all of that detail again, but here's a reminder that we can see the accretion disk, the matter that is sort of waiting to fall into the black hole in the center of the galaxy M87. This is a rather large supermassive black hole, SMBH. This is 6.5 billion solar masses. We use solar masses as a unit simply because tons or kilograms would be a bit silly, so we just use multiples of our sun's mass, and this one is 6.5 billion solar masses. There's also a supermassive black hole at the center of the Milky Way galaxy. That's a little bit smaller, 4 million solar masses, still huge compared to the result of a single star collapsing, and it's still a matter of debate as to how these black holes come to be. The James Webb Space Telescope is looking back in time to the very early universe to try and figure out, how do these black holes form? How do we end up with black holes that might be millions or billions of solar masses relatively early on in the universe. Understanding how that can be. Is it simply that lots of stars are born and die and generate black holes and all of those black holes merge together? There doesn't seem to be enough time for that to happen. So how can you go from essentially nothing to billions of solar masses on such a relatively short time scale? Again, I'm not going to talk about the detail because warping space and time is a talk I gave a few years back. So let's just do a graphical summary of what I've been talking about. If we start with a giant molecular cloud of hydrogen, hydrogen probably enriched with a few other elements as well, but let's just assume it's hydrogen for the time being. The collapse of that under gravity might produce a small star like our sun. When the sun eventually comes to the end of its life after billions of years, it will swell up into a red giant, and because the gravity is not particularly strong, the outer layers of the star will be sloughed off in order to produce a so-called planetary nebula, comprising mainly hydrogen and other elements that were in the star in the first place. What's left when you slough off the outer layers of a red giant, the core that's left, is a white dwarf, something about the size of the Earth, but rather hotter, which will eventually cool off given time. It is also possible that the collapse of a giant molecular cloud might produce large stars. Again, trying to understand, if you've got a cloud of hydrogen, how many big stars do you make, how many small stars do you make? That's an important part of understanding clusters and galaxy evolution. But if we make a large star, what's going to happen? Well, remember, it's going to come to the end of its life rather sooner because it's going to need a much faster burning of its fuel in order to compensate for the gravity. And if the star is massive enough, it might end its life in a supernova, and it will again redistribute a lot of the matter of the star back into the interstellar medium, and the core that's left could be either a neutron star, or if gravity is strong enough, could be a black hole. So regardless of whether the end result of a star results in the death and the result of a white dwarf, a neutron star, or a black hole, remember that a very large fraction of the mass of the star actually gets recycled via a planetary nebula or a supernova remnant, and a lot of that material gets recycled back into the interstellar medium, where we are then ready to make new stars whenever there's another trigger, whenever there's either a supernova producing a ripple in the cloud to generate a new star, whether or not the galaxy collides with another galaxy and produces shock waves, which makes that cloud collapse once again. So there is always this recycling of material, and it will happen on time scales of millions to tens of millions to hundreds of millions to billions of years. So over the lifetime of the Milky Way and the lifetime of the Milky Way in billions of years to come, this cycle, this recycling of material will happen again and again and again, and will continually enrich with heavier elements the original material from which we make stars. So I guess the take-home message is we have some understanding of stellar evolution. The details, the real details, are very complex, but I hope at least from this evening you've got the idea that we can understand the basics of stellar evolution if we just get a hold of those three factors, the A, B, C. Thank you all very much.